Yeah, welcome back to the session. So, yeah, our idea was to identify the key set of best features from the given set of n features that will preserve the information loss by using this formula. Okay. So once we get these k features and once we get we can get back the reconstruct the original point. That is the x bar, and our idea is x minus x bar or x cap. The gap should be very low. That's nothing but information error. Right. So the principal components are dependent on the units used to measure the and the one of the limitations uh, of this principal component is what kind of features we are using and their units, what especially their units. Is matter. Suppose if you are talking about the weight, if I am saying, so somebody may consider in the kilograms, or somebody may consider in uh, what I mean that the different measures of the weights, like uh, what I mean the metric, something different measures. Okay? So then the values will different, right? So then that is also matter, as well as the range, as well as the range. Okay, some features. If I'm talking about the percentage, okay, that is the range from 0 to 100. So if you're talking about the salary, so there a range is beyond 100 also. Okay, so uh, there is no uniformity. The overall, what I want to say that there is no uniformity. If there is no uniformity in the range and the units, that may impact PCA performance. So that's why we have to do the data normalization so that all be in the similar range. Okay, like 0 to 1 or 0 to 100. So the data should always be normalized prior to using PCA. Okay, that's important of it. And a common normalization method is to transform all the data to a zero mean units. We already know how to transform the data into the zero mean data, that by calculate the x bar and subtract from the x. Yeah. X minus x bar we did in the very beginning, okay, earlier. So now how do we get the unit standard deviation data? Means if I take the standard deviation of the data SD, so it should be 1. Okay, so how do we get such a data? Zero mean data we can get it when I subtract the x bar and when I subtract x bar from every point. Calculate x bar is the mean of all the points, and if you are subtracting x bar from every point, then such a normalized data, if you are finding the mean, so definitely it will be 0 unitical. And what is the unit standard deviation data? So how do you get it? We will see now by dividing into. So how do we normalize? Where xi you know, and mu you know, that is x bar. So x minus x bar, and this you have to divide by the standard deviation of the data. So first you have to subtract the mean, and whatever the value you will get, that you have to divide by the standard deviation of the data. The resultant data will have the zero mean as well as the standard deviation is 1. Okay, let's see some of the application of the way this very used this principal component as for the not only for the dimensional reduction, some application which relates in the areas of the image processing. The goal is to represent the image in the space of the lower dimensions using the PC. Obviously, the purpose of PC is to discuss the dimensional to reduce the dimension. It's useful for the various applications like face recognition, image compression, and also so where in order to identify the face. But the thing is, should be the face should be in the it should not be corner of this. It should be at the middle of the picture. Then we can identify the face in those applications. Of course, nowadays we are using the deep architecture for the face recognition and all this stuff. But the prior to that, we have used the PCA for the face recognition too. So obviously, we can once you identify the important features. So from that features, we can constitute the original image. Okay, so reconstruct. So that is where we can use image compression. So given an image of size n cross n, suppose I have given an image as m images of size n by n. So each image of size n cross n, how many such images are there? M images are there in my data set. The first represent each image as a 1D vector. What we are trying to do, this n cross n, I'm doing image flattening. This is called image. The flattening means I am converting into the n square cross 1. So a single vector which is of uh, 1D vector which consists of n square cells. Okay, the vector. Note that the face recognition faces must be centered and of the same size. So if you want to apply for the image recognition, apply the face recognition, apply applications where image has to be at almost all center, not the corner, so that we can easily detect the face. Otherwise, whose face it is different. Whether it is a face or not, we can do the face recognition. The key challenge is that the covariance matrix sigma is now very large, because earlier if you want to compute the sigma x, right, whereas it is a 1D vector of n square, which is the features. Now, how many features are there here? N square features. So, what is the dimension? It is the n square cross n square. If I want to find out the sigma x, which is of n square cross, the dimensions of this matrix is n square, because every feature and with other feature you have to find the covariance matrix. Because if you want to get the characteristic equation, so you have to find the sigma x. Because if there, I think I said sigma x into lambda ui is equal to lambda I into the ui. This is the my characteristic equation. To solve, you will get the eigenvectors. So how can we compute? Okay, of course it's a very because the size is very huge, especially when you're talking about the high resolution images. It's very difficult to compute. Okay, we will see what are the remedies for that. How do we solve it? Okay, compute the covariance. As you know, for the time being, I am computing the covariance matrix. Okay, how even though it is difficult, we are computing. Sigma is now as an unsquare n-square matrix. The computational expense to compute its eigenvalues and eigenvectors too. Right? Now, what we are trying to do that, we will use the simple trick to get around this by relating the eigenvalues and eigenvectors of A to those of A transpose to the A. So let us talk about what is this A. Okay, so this is actually the how you can get the covariance matrix. So I am slightly modifying this with a matrix called a matrix called A, where A is the phi 1, phi 2, the transformation phi 1, phi 2, and phi m. So how many such uh, uh, where is m is the where is m is number of images, where n is the number of images, isn't it? The number of images. For every image, we are finding the phi 1, phi 2, the phi m. So once this is A and this is A transpose. So when you are when you are finding A into A transpose, actually you can rewrite this equation. You can rewrite this equation as a 1 by m into A transpose, where A is like this. But A into this is the original covariance matrix calculation, but it's very expensive. But if I slightly change A transpose to the A, if I just I'm doing reverse A transpose to the A, this is very easy to calculate. Let's see how it is. So we will use the simple trick to get around this by relating the eigenvalues and eigenvector of A transpose to those of A transpose. What is the difference? Here A transpose is the first, here A transpose is the next second. So let us consider the matrix A transpose to A instead because now actually it is A into N transpose. Now we don't consider A into N transpose. We are considering it's reverse. Okay, just transpose. Okay, A transpose into A. So let us suppose eigenvalues and eigenvectors are something like this. So if this is eigenvector and this is eigenvalues, then we can get the characteristic equation like this. So this is our what is this? Sigma x. So sigma x is equal to A to A, and this is what is eigenvalue? Eigenvalue is mu I. So this is mu I, and this has to multiply with the eigenvector, and this has to multiply with the eigenvector. So this is my characteristic equation. So now with the characteristic equation, what I am trying to do that here, the multiply the both the sides by a I am trying to do a, and this is my characteristic equation. I am multiplying, so a into a. Now let's see. Assuming a into a transpose and mu I is equal to the lambda into a. Where you got this lambda into mu I? This lambda is the eigenvector. A into a transpose we already know, right? A into a transpose. Okay, this is the original eigenvector is mu I, eigenvalue is lambda I. the original case. But in this case, we are mu I and vi, but in the original case, lambda I and mu I. Okay. Now, here in this case, lambda is equal to mu I. Of course, the mu I is equal to A into vi. So, if I am comparing with those two equations, we compare with those two equations. So, in that case, lambda is equal to mu I and mu I is equal to A into. We already know what is A. In the previous diagram, we already came to know A is a phi 1, phi 2, and phi n. But do A into A transpose and A transpose have the same number of eigenvalues and so because what we are doing is we are instead of A transpose A into A transpose, we are using A transpose easy to reduce the computation. That the whole idea is to reduce the question is does both have the same number of A transpose into A can have up to n square eigenvalues because the dimension is n square cross n square eigen. But whereas A transpose A where A is of size m can have up to m eigenvalues because where m is size m cross n. So it can be shown that m eigenvalues and eigenvectors of A transpose into A are also the m largest eigenvector values are m vectors of A into A transpose. So what are the eigenvectors you will getting from which is whereas m is far less than n square, what are the eigenvector which is getting by A transpose into A, which are the top eigenvectors of the a matrix which is generated A transpose of A, where the eigenvector which are calculated from A into A transpose, you are get n square eigenvector. So there is a repetition. So what are the eigenvectors are there? M eigenvectors will present here also, but those are the top eigenvectors, which is the highest eigenvalues. Those are highest eigenvalues. So M, the largest eigenvalues, of course, the M largest vectors. So what is we are trying to do that at least we are finding the m largest eigenvectors and correspondingly we can get a largest value and correspondingly we can get the m eigenvectors easily. Step 5 so need to be updated as follows. If you want to reduce the process, because this is the scenario where we have a images. This is a problem with the image. So one thing we can notice that if we are dealing with some simple images, we are feeling to compute. We are feeling difficult to compute the sigma x, which is the covariance matrix. Now we are dealing with the big data and the deep learning environment. What is happening is we are dealing with in a high resolution images that in huge number. In those cases, the computing of sigma x is more and more difficult. So that's the reason we people are made this process automated so that the deep architectures will automatically retrieve these best features that will improve the performance of your model. Okay, so now let's see how we can apply the PCA on some sample data set. I will explain through in Google Colab now. So I think yesterday I discussed how to open the Google Colab and all. This is there are two type of cells, code cell and text cell. Now here I am importing some important library functions like NumPy. So NumPy basically having the function which support the matrices like matrix transpose or matrix inverse, covariance calculus, basically linear algebra stuff is available in the NumPy. In the pandas, of course, it's the stuff related to the data frame dealing, like processing of the data frame, reading and updating the data, reading the columns, number of columns, what the data available in the data frame, and all this stuff is we can process using pandas library. And for visualization, we can use matplotlib. And there is another visualization. Seaborn is much more advanced. What I mean that. Function that supports the data visualization. So these three basically providing the libraries for the data visualization. Okay, so let us compute that. So I am computing this cell. So it is running now. So once it's successful, no bugs. So it will you can find the a tick mark in the green color in the left side of this run button. If you yeah, so if you see, so it took 8 seconds and there is a there is a green color. Yeah, this is. So if you look at it, this took 8 seconds. There is a green color button beside this. Next, I am loading the data set into my Google Drive. What I used yesterday, same I am using. So the diabetes.csv. So this once I read it, so import IO and the data frame is equal to pd.read underscore query, because read underscore is CSV is a function which is available in the pandas library to read the CSV file. So this I am executing, right? So now the data is available. Let us check it whether the data is available in my programming environment. So that's the reason data frame dot head to show the sample data. Yes, in this data we have 8 features, 1, 2, 3, 4, 5, 6, 7 and 8. And the last feature is the class decision attribute. Okay, this. Just I want to find out the what are the column names. Okay, pregnancies, glucose, blood pressure, BP, skin thickness, and all the stuff. So some statistics I am getting, like what is the number of samples and number of dimensions in my data set. Like there are 768 samples and 9 dimensions. In that one is the last one is the, so this outcome is the class level decision variable. Remember it. So what is this data from the core? It compute the pairwise correlation of the columns. Correlation shows how the two variables are related to each other. Positive value shows as a one variable increases, other variable increases as well. Whereas the negative value shows that the one variable increases and other variable decreases. So bigger the value, more strongly two variables are correlated and vice versa. So that's about the correlation concept. How do we compute this covariance? Sigma x you can easily compute by using NumPy library. We'll see now. So before that, I am separating because why I'm separating, because y is a the last column, the decision variable is not a feature. That's why I'm separating. It's need not to calculate covariance for that feature. Okay, so that's why I reason the first 8 features, starting from this pregnancies to the age, I am putting an x variable data frame, and the last the decision variable stuff kept in the stored in the variable called y. Now let's see the x, so that whether the data is properly retrieved or not, whether does it have a decision variable or not. So let's check it. Yes, there is no decision variable. They have 6 attributes. So check it just to cross verify. Yes, it has about 8 attributes. The shape is of x is of 768 yes 7. Now let us compute the data standardization. So what I told you that before you want to apply the PCI, your data should be normalized. So for that I am using standard scales, a kind of normalizer to transform data to 0 to 1. Okay, kind of normal distribution. So now this is x underscore std means uh, we have transformed the data by using some normalization technique. So if you look at all the values are from 0 to 1 or some -1 to 1, whatever, normalized. So suppose just class verify it's an MPS. Post same whether same number of samples are there to the original X and X underscore STD. Yeah. Now the actual part, now the modified version of the data is X underscore not X. Now X has been converted to X underscore STD. Now this we can use it for the computing the mean and the covariance matrix of the sigma X. The sigma X of X under, so this is sigma X how we are calculated. So using these two formulas, we can calculate sigma. So this is covariance matrix. We can see the covariance matrix. If you look at the diagonal, it is always 1, 1, 1, 1. Okay, we are 1, 1, 1. Okay. Just I want to check. It should be 8 cross 8. NP dot shape covariance underscore. The size of the covariance matrix is equal to number of features. Okay. NP dot shape. Hmm. The 8 class set is number of features, right? So this is a covariance matrix. So a covariance matrix in more visual form. So if you look at the principal diagonal is always the one. So they have, because we are finding the coefficient same variable, so it is always one. Now what I did here, the eigenvalues become the covariance matrix. Then what we did, we want to find out the eigenvalues and eigenvectors. Let's see. So there is a function in the NumPy is called uh, a linear algebra, so np.linearalgebra.eig eigen. Just give a covariance matrix the input, it will give the output as a eigenvalues and eigenvectors. So if you look at here, it has given the eigenvalues, okay, 2.097 and all the stuff. There is a 1.7 and 0.4 and 0.40, 0.6 and 0.7, 0.8 and 1. So then you have to arrange them in a descending order. You have to arrange the first highest to the lowest. Okay, so you have to arrange them in the descending order. So here we are doing a descending order and corresponding. Once we have arranged the descent, the corresponding eigenvectors I am considering. Corresponding eigenvectors we are considering. Now just after sorting in the, so first one is 2.09, then 1.71, 0.8. Okay. Now, so if you look at, there are 8 eigenvalues. So because the number of features are 8, you have it. But our intention is not to keep all the eigen features. So out of these 8 features, how many features we have to consider so that I can retain the maximum information. So for that, what you can do is you can calculate the variance percentage. Okay, variance percentage. So what is the contribution of the each lambda towards the preservation of the information? So if I, by looking at this plot, I can say that the principal component 1 is contributing 25%, and this is about 20, and this is 2. The alone the feature, because this component is, because this eigenvector is contributing around between 10 to 15, and this is 10 to 15, and this something like so. Basically, if I want to preserve the maximum information, so if it is enough to retain first 5 features or first four eigenvectors, or if you want to keep maximum information only first 2 eigenvectors, is retaining the maximum information so that we can keep only those 2 eigen vectors, so that when I'm transposing a point into the space where these 2 components, the first and second principal components, are the basis vectors, so that we can preserve the almost 50% of information. The plot above clearly shows the maximum variance somewhere around 30% can be explained or achieved by only the first principal component alone. The second, third, fourth, and fifth principal components share almost an equal amount of information, comparatively 6 and 7. Yes. So 6 and 7 components are share less amount of information as compared to the rest of the principal, but those information cannot be ignored since they both contribute almost like 17%. We can get here both 17% of data, but we can drop the last component as it has a less than 10% of variance, because what percent of variance is contributed by each and every principal component. So when I sum it up, so if I say 90%, so when I sum it up, the summation of all this information preserved by each and every component should be greater than 90. So like that. So in that case, we can um, identify the, so what is this is another kind of data visualization. So the principal component only one, if I say it is preserving almost all 30%, and when I consider 2, it is preserving I mean that around 50%. So if I consider first 3 largest principal components, it is preserving almost all 70. So if my consideration is 90, then you can cut it down, then 5. So when if you look at, you go x-axis, then you will get 5. Means if I consider the first 5 best components, first 5 principal component, the first 5 principal component, so that is preserving the maximum information around above 90. It is, so this is the cumulative the information preserved by the what I mean that our principal components, largest principal components. Okay, so if typically speaking, the first 5 principal components. So I can, if I want, our intention is to preserve the uh, Our intention is to preserve the 90% of the information. Just is enough to consider the only 5 components, first 5 components to preserve the 90% of information. Okay. So this is it's a kind of different cumulative variance of the component. The above plots almost 90% information by first 6 or 5 components, or first 5 or 6 components. So you can ignore the 7th component. So once we ignore the 7th component, suppose here can consider, I think, first 6 components. Then I'm considering the first 6 components. Then I'm transforming my data. So how I have to transform my data? So once I get the number of components is equal to 6, then the sklearn PCA, that is, so this is my you have to transform the data x underscore std. Means x underscore std. What is the dimension of x underscore std? Go back to this x underscore std. It is, I think, 768 cross 8. Right. Now let us check it. What are the dimensions? Yeah, this is not this one. Yeah, this video. Yeah. So I think here uh, number of one. Here I consider only two principal components, because I feel that only 50% of information. So this first component is 26, I think, around, and this is around, say, principal component alone 2 is preserving around 23%. So altogether, if I only consider first two principal, it is enough that the 50% information is preserved, just for example. So if I consider only first two components, so then I am considering only first two top eigenvectors. These are two eigen. So when I am multiplying with this your input data, when I am multiplying with my input data, so x underscore t dot product with a matrix underscore w, which is a transformer matrix tree. So then your data will be transformed to the y. So where y is a, what is the dimension of the y? What are the dimensions of the die? So yeah, we can check it here. Yeah, this next time. So np dot shape of y is showing that 768. So what we did, say data which is of 768 cross 8 is being transferred to the 768 cross 2, where 2 is the number of eigenvectors. So the eigenvectors are the principal component. How many principal components are there? Guys, how many principal components are there? Actually, 8 principal components are there, but we picked the top 2 principal components, which are preserving almost 50% of it. Suppose if you want to preserve the 90% information, the number of principal components will be changed, like 6 to 5 to 6 and all. Okay, this all depends on what is your the requirement uh, uh, of your problem and your our application and all this stuff. So any doubts so far, guys? Okay. So yeah, we have discussed about the principal component analysis and how we can implement the PCA the step-by-step fashion using uh, NumPy and Pandas libraries in the Python. Okay, I have explained in the Google Colab. Now let's see all these things. Okay, we have seen one trick for calculation of sigma x, where the sigma x, especially this problem will arise when we are dealing with the high resolution images, because where the sigma x is very become difficult. So where we have used instead of calculating A into N transpose, we are considering the A transpose into A. One remedy is this. Okay, so this is the visualization. Suppose this is my original data set. if you look at all the faces, if you look at all the faces are at the center of the image, and let's see how a face look like. What I'm doing, I'm finding the mean of the image, and uh, this is the mean of the image. Uh, and of course, the top eigenvectors, the eigenfaces, we can call eigenfaces, the mu1, mu2, how they look to be. It is preserving the maximum information. If you look at 1, 2, 3, 4, 5, 6, 7, and 8, okay, this is u1, u2, u3, u4, u5, u6, u7, and u8. And if you look at these first three eigen features, are preserving the important information. If you look at, okay, when I get the eigenfaces for all the eigen values, eigen vectors information, when I reconstructed the image, if I look at the first three, are preserving the more information, so that it is enough to consider only three-dimensional data. I mean, you can transform to the three dimensions instead of the 8 dimensions. So this center not required. Now let us see the another application of the PCA is face detection and face recognition. Okay, so this is the work which has been carried out in the early 90s. Turk and Penteland, there's a in the journal of, which has been published in the Journal of Cognitive Neuroscience. Uh, the topic of the paper was the eigenfaces for the recognition. And this was the details of the paper. If those who are interested to read, they can read it. So let me explain in briefly what this paper is all about, how they have used the PCA for the face detection and face recognition. The face recognition, the simplest approach is to think of it as in a template matching. Of course, if it is matching with some particular template, we can say it's a face characteristic, face template, then we can say face. The problem arises when the performing recognition in a high dimensional space. The recognition means when exclusively when you are. I told you that one of the limitation of when you want to apply the PCA, the face should be in the centered. Okay, it should be sure. Then only it will detect it. Otherwise, it will detect, but the accuracy is very low. The problems arise when we are performing recognition high dimensional space. To use the dimensional reduction. So the process the image database, typically referred as the training phase, they're doing the computer PCS space using the image database, that is training data. They represent each image in the database with the coefficients. So what I'm trying to do that every image is on every image. So what they did is in every image there is a n cross n. So on this image they applied the PCA. So you will get how many features? So n square features you will get it. So we have a n square features over here. They represent each image of the data set with the k coefficients. Okay. Now I'm saying important features we are identifying, and I'm saying that those important features as a k, and those are called k coefficients. Okay. So that is not what k features, gamma by 2 and yk. Given an unknown face x, so what you have to do is you have to apply the PCA. So step subtract the mean face of the x bar. So the first and foremost requisite is you should be data should be uniform. So for that you can get the zero mean data, so that you can calculate the x bar, and from that you can derive x bar from a given x, so that you will get zero mean data face. So project the unknown face into the eigen space. Okay, what we are trying to do that we are trying to project the what are the unknown face. I mean, this is face unknown face by using the eigen space. I already computed the key eigen values for each and every face. By using this, we are trying to project into the new space by using this formula. So y is equal to pi transpose into a. Then you will get a face. So this face you are doing the matching. Okay. So that is called sigma. Then closest match of sigma from the training set. You can find the uh, already your data set is on the data set you already computed. For every page you computed k features, right? So you are finding the closest match from the given transformed spaces. The given face which is of cross n cross n has been transformed to the k cross 1, then this k cross 1 is performing the what I mean that pattern matching or template matching. So whichever is closely matching by using Hamming distance also we can say is whose face it is, whose one it is, face recognition. Okay. So whichever whom is matching, you can say, or you can use Euclidean distance or Hamming distance, or Mahalanobis distance, whatever the distance measures, you can use for the similarity the measure. So what we are trying to do that, see how cleverly they have applied the PCA for the face recognition. They have applied on the PCA on the training data set, and so what are the features it will get? K features have been stored in a database. They have been stored in the database. Okay, so this database is we are matching with the, if a new face comes, we are transforming into the K's dimensions, and those K dimensions we are matching with the any one of these faces which are having in the databases the closest match, either using Hamming distance or Mahalanobis distance, whatever distance. So those are similarity measure, how close you are face to the other. So based on that, we can identify the those faces. Right. This is a if a given image. Okay, this is a given image. Uh, Detection of the face. Okay, we are detecting this. This is the one face object detection. Like, okay? Okay, this is the object detection or face detection. But face recognition is different. The detection of the face and recognition is whose, whether it is a Swami face or it is a Venki's face, it is a Manjaya's face or it is a Vijay's, whose face it is, whatever depending on the characteristic of the respective person's face features, we can identify that. Okay? So yes, it's Sally's face. So how can we use same database or the PCA for the identifying or recognition? We know face detection we are doing, but face recognition can we do? Yes. Given an unknown image X, follow these steps. What is that they are doing? You subtract X bar, then project face into the eigenspace and compute the Euclidean distance. If we compute the Euclidean distance, which is the compute the Euclidean distance means what is the distance between the original face to the transformed space. But that means how much information is preserved. Okay. So this is my original face and this is a transformed image. So what is how much? So 5 minus 5 bar is the Euclidean, how much similar both are. Okay. Now, so the distance ED is called the distance from face to the face space. Okay, the transformed space you can say. If the ED is less than certain threshold, then X is a face. The X is a space, and X is a face. Otherwise, it is not a face. So this is a problem of the face detection. Okay, and the face recognition. Yes, using we can recognize. How do we do? By finding the closest match, we can do the recognition. Slightly modifying this algorithm, we can use the face detection approach also. Okay. So what's when I'm doing the PCA for face detection and what I mean that face recognition, it has certain limitations. One is the background changes may lead to some other problem. Okay, so D applies outside of the face by multiplying the input image by a 2D Gaussian window centered with the face. Okay, so what we are trying to, we are working around this problem. So we can use some kind of filter called Gaussian filter, 2D filter. Or so that will when I rotate over on the face, then uh, I can reduce the impact of the background. So light changes degree of the purpose. When there is a impact of the light on the face, that then also it will impact the. So there are certain things that will degrade the performance of the face detection and recognition if I use the PCA. Performance decreases quickly with the changes to the face size. So if I face size small or medium or large, depending on the face size, scale input image to multiple size, multiple scale eigenface. Perform decrease the changes to the face orientation. Face orientation is also matter. So PCA is not always an optimal dimensional reduction technique for classification purpose. If you say that PCA is, we can say that if this would be the best, good one, then there is no existence of other algorithm. But the PCA is not always an optimal dimensional reduction. There are still some other techniques which work better than the PCA, exclusively for the classification purpose. Okay? Now if you yeah, this is the best example between the hmm. There is other technique called LDA. In the LDA, it works like this. So there is a data. So there is a data. If this data has been projected into the line is like this. The data has been projected into this line. If you look at the points over here, they are not well separated. Suppose the same data, if project the same data has been projected in this direction, the same is projected in this direction, or any point in this direction, any line in the direction. So we can get, if you look at, there is a clear distinction between this group of samples and this group of samples. So this is called class discriminated information. Means, so our idea of the LDA is to find out this line such that when I project all the points onto this line, so I can differentiate all the points cleverly. So that is all about the LDA, linear discriminant analysis. Okay. So whereas in the PCA, I think there is some problem. Okay, just I'm stopping my discussion by throwing just introduction to the LDA. Okay, we have only few minutes left. Yeah, any queries, please? So yes. Hello, guys. Any doubts regarding the dimensional reduction? But nowadays, these things, whatever I said, the PCA we are applied explicitly, but to identify the best combination of the feature, best set of features, the k-best best, k-best feature. But now, especially in the image processing, is very difficult of the PCA, and just now I shown you. So to overcome this problem in the deep architectures like CNN and all this stuff, there we are automatically, by applying the convolution and pooling and operations, we can automatically get the features. Okay, so the beauty of this CNN is, the beauty of this deep architecture is they will automatically extract the important features. Whereas here we are manually identifying or some programmatically we are identifying systematically using PCM, we are identifying the best features, but there we can automatically identify. Yes, take questions, please. Yes, guys.
Thank you very much, sir. Thank you for your valuable session.
Yeah, if you have any thoughts, please let me know. Otherwise, I will close the message.
Hello, sir. Is my voice audible?
Yes, yes, yes.
I hope we have one more session, right, sir?
So, yes, one more, but not today, I think.
Yes, sir. Not today, not today, not. I know it.
Yeah, it's on Monday. Yes, yes.
Okay, sir. Okay, sir. Thank you very much, sir. I
Mm.
mean, hopefully,
Okay, thank you, and
okay, sir.
so
Okay, sir.
have
Thank
a
you, sir.
great weekend. Bye.
Participants, you may leave.